So I'd like to teach you about something called Lewis dot structures. Now, Lewis dot structures are luckily pretty simple to understand because they themselves are simplifications. So Lewis dot structures are a visual representation of only the valence shell. I think you've seen at this point that despite having a very large electron configuration for most elements, the most exciting stuff, the most exciting things happen in the valence shell. So it's just a way of kind of boiling back the information that we're getting and really only talking about the most important elements for each element. Again, it's really another way of communicating the really important information about an atom quickly and very visually. I want to give you a little bit of an example. Here is a Lewis dot structure for oxygen. And you can kind of see very quickly that it isn't as robust as what you might be thinking for what an electron configuration would be. Here is the electron configuration for oxygen. It's 1s2, 2s2, 2p4. And yes, that's a lot of really good information, but the picture is much, much, much simpler. Now remember that a Lewis structure is a visual representation of only the valence shell. So let's take a look at that valence shell. Valence shell is whatever coefficient, that's the big number down in front, is the largest. And in this case, that's the second shell. Oxygen has 6 combined total valence electrons. And notice that the picture also has 6 dots. So I'm hoping you're figuring out what a Lewis dot structure really is. It has 2 components to it. First, there's an element symbol on the inside, and then around the outside, we draw the valence electrons as dots. And there seems to be some sort of a structure or a pattern to how I have those drawn in. And in fact, actually, we're going to follow just a couple simple rules. First of all, we're going to follow that octet rule. So the maximum number of dots that we're going to draw around any single element symbol is 8. We are only going to limit ourselves to 8 valence electrons. Also, electrons tend to kind of flow in units of 2. They tend to be paired. So we're going to pair them in groups of 2 per side. Now there's 4 sides to each element, top, bottom, left, and right. So there's a maximum of 2 dots per side. And we're also going to follow Hund's rule. So we're going to put 1 dot on each side until we absolutely have to double them up. In this case, if I had 6 valence electrons, that was enough to put 1 dot on each side, and then I was able to double up on 2 sides. Now I'm not going to be too picky about where the doubles go and where the singles go. As long as there's 2 paired sets and 2 singlets here, I would be completely happy as accepting this structure as being correct. I want to show you a couple more examples of some Lewis structures for atoms. Here's phosphorus with 5 valence electrons, chlorine with 7 valence electrons, and argon with 8 valence electrons. Again, notice that all of the electrons are only doubled when they have to be. So it's okay to have 1 valence electron on each side. And I'm hoping you're also getting from this image, it really doesn't matter where the doubles go or where the singles go as long as they exist. So let's dig a little bit deeper again into this whole Lewis structure business. So here we have oxygen. Well, what if oxygen wanted to become an ion? It has 6 valence electrons. If it became an ion, it would need to gain 2 electrons. I'm going to start by modifying the electron configuration, gaining those 2 electrons in. But now this also has an impact on the Lewis structure, since the Lewis structure is a visual representation of that valence shell. I'm going to also have to add in 2 electrons to it. My final image is going to look something like this. Now I have my 2 extra electrons colored in a different color, but if you just have an ordinary pen or a pencil, there's really no way of distinguishing which ones you've added in and which ones were there originally, and that's just fine. But notice there is one key feature now that just got added in. We put in a set of square brackets, and we're also indicating its charge. Square brackets around a Lewis structure indicates that that Lewis structure has been modified in some way, either by adding in electrons or by removing electrons. So anytime that you monkey with the natural number of electrons around the outside, you're going to need to use those square brackets. Now, outside of those square brackets indicates how you monkeyed with it. -2 charge means I added in 2 electrons. So this is what oxygen ion would actually look like for a Lewis structure. Now, typically, you're going to notice that negative ions tend to have completely full outer shells. So they'll typically like to fulfill that octet by having those 8 electrons around the outside. And I just wanted to show you a couple more examples. You're going to be doing some for me for your homework. But here's nitrogen, chlorine, and sulfur all as ions. Now, although their atomic Lewis structures are going to look different, their ionic Lewis structures look the same. And that's because these things look a little bit more isoelectric. Again, they're going to have similar electron configurations on the outside. Notice in all of those cases, though, they all have square brackets saying I've monkeyed with the number of electrons, and they've specifically stated the how. So nitrogen, you've gained 3 electrons, chlorine, you've gained 1 electron, and sulfur, you've gained 2 electrons, all indicated by those negative charges. It's a little bit of a flip-flop in the brain to think that a negative charge means you're adding in an electron, but I'm sure after a couple problems you'll start to kind of get used to that. Let's take a look at another example. Here's magnesium, both its electron configuration and its Lewis structure. So magnesium here only has 2 valence electrons. Well, when it wants to become an ion, it's going to eliminate those 2 electrons because it could either gain 6 or lose 2. It's much easier just to lose those 2. So again, I'm going to try and use my square brackets, indicating that I've modified my structure. I'm going to take those 2 valence electrons away and then indicate outside of the brackets how I've changed it. I've removed 2 negative charges, which means that what's remaining has a +2 charge. Magnesium is a 2 positive ion. And again, we show it kind of completely devoid of where the valence electrons used to be. Now, positive ions tend to always be depicted in this way. They tend to always have empty or formerly empty valence shells. Of course, we now know that the valence shell is now 1 lower than that and is completely full, but we're dealing with its previous valence shell here. Very typical of how you would actually depict all of these beautiful ions. And again, just so you can kind of see that we're not crazy, here are a whole bunch of different images of positive ions Lewis dot structures. You can see in common, all of them are depicted as having empty valence shells. They all have square brackets and indicate the how that actually occurred. Sodium here with its +1 charge means that it lost 1 valence electron. Aluminum with its +3 charge means that it lost 3.